Welcome to the course on computer design of electrical machines. We'll have a lecture 7 today on transformer design part 4. So to start with the outline of the presentation, we'll talk today with the transformer design example as an analytical problem, and then we'll go of course some application, both other kind of transformer like high frequency transformer, then multi-winding transformer. Then we'd like to of course cover the computer design of transformer, followed by numerical exercise and references. So coming to typically a design example of the transformer as analytical. So with the statement as the example one, design a 100 kVA 3-phase 50 Hz 100 kV by 440 delta star self oil cooled with transformer rise temperature not to exceed 40 degrees Celsius. The no load loss is 350 watt and copper loss and state loss on full load is 2000 watt. The percentage impedance is 4.5%. The induced EMF per turn is 4.45 volt. Calculate also the no load current efficiency at degrees centigrade at full load 75% of unity power factor and regulation at 75 degree at unity power factor. So coming to the solution, the specific magnetic loading. Let's consider magnetic flux density 1.35 Weber per meter square, and material for core can be hot rolled steel lamination. So specific current density to be taken as your delta at 2.5 ampere per millimeter square. So now coming to cross section of the core, that net iron area equal to A equal to ET upon 4.44 FBM. Putting the value, it comes 0.015 meter square, and gross cross section area AGI is AI upon stacking factor, considering a stacking factor for lamination 0.9. So putting the value, it comes 166.83 typically centimeter square. And let us choose a 3-step core, diameter of subchromatic circle, that comes AI equal to 0.6 d square. So just as an example with the dimensions as shown in the figure like ABCD. So here cross section area, you can call it the, from that we can find out the D, that is the diameter of circumferring circle, it comes AI upon 0.6. So just putting a value, it comes 15.82, that is around 16 centimeter. Then we get a dimension D equal to 16 centimeter, then A equal to 0.9 D 14.4 centimeter, and B equal to 0.97 D 11.2 centimeter, and C equal to 0.42 D 6.72 centimeter. For minimum, you can call it the maximum steel what we can put in the ceramic circle as a core. Now coming to as a design of window, Q equal to 3.33 FBM AW KW into delta into 10 power minus 3, and window space factor is the copper area in window divided by total window area. So considering the window space factor typical KW 0.25, then the window area is AW equal to Q upon 3.33 FBM AI KW delta into 10 power minus 3. So putting the value, it comes 4.474 centimeter square. Now let's the ratio of the window to height, which is one parameter, of course depends on many factors which we discussed already in earlier lecture. Considering 2.5, as you can see the dimension here. So AW upon WW is 2.5, and AW is AW into WW 474, and keeping the value of 474 into 2.5 W square, then W comes 13.8 centimeter, AW comes 34.4 centimeter. Now coming to design of yoke, the net area, iron area of yoke is 1.2 AI, so it's equal to 1.2 into 150.15, so it comes 180.18 centimeter square, and gross yoke area is net iron area divided by stacking factor. So taking a lamination stacking factor 0.9, so it comes 200.2 centimeter square, and flux density in yoke is typically, we can call flux density in yoke by 1.2, so it comes like 1.125 Tesla. Now assuming the yoke to be rectangular as shown in the diagram, so depth of the yoke is largest stamping of the core, that dy equal to A, that's a 14.4 centimeter, and height of the yoke is just by equal to Ay upon Wy, that's a 200.2 divided by 14.4, it comes 13.9, that's equated to 14 centimeter. Now coming to overall dimension of the core, that is distance between the adjacent core center, D equal to W plus small d. Putting the value, it comes like a 29.62 centimeter. and overall width W equal to is 2 capital D plus A. So putting value, it comes like a 73.64 centimeter, and overall height, that is equal to HW plus 2 HY. So putting value, it comes 62.4 centimeter. Now coming to overall dimension of core, that's a depth of the frame, that is dy equal to A, say 14.24 centimeter. Now coming to design of windings. So first let us say A take a low voltage winding. So line voltage on LV side is 440 volt, is star connected. Phase voltage now comes like your line voltage divided by root 3, or that's 440 divided by root 3 volt, and number of turns per phase will be that, but volts per ET is given 4.5, so 254 by 4.5, it comes 56.4, that's we can round off to 57 turns. Now typically now current per phase is I2 equal to kV upon 3 into V to phase. So putting a value, it comes 131.23 ampere. And area of the conductors of LV winding is say I2 upon delta. So putting a value, it comes 52.49 millimeter square. Now coming to design of HV winding. So in HV side, we have a line voltage on HV side 11 kV, and delta connector, the phase voltage is same as line voltage, that is 11 kV, and number of turns will be now T1 equal to V1 upon V2 into T2. Putting a value, it comes like a typically 2468.5 rounded off to 2469 turns, and current in HV winding I1 equal to kV upon 3 into V phase. So putting the value, it comes like 3.03 ampere. Now coming to area of the conductor in high voltage winding, that's a I1 upon delta. So putting a value of, it comes 1.212 millimeter square, and diameter of conductor is 4 under root 4 upon pi into area of winding conductor. So putting value, it comes 1.242 millimeter. Now total copper area in window, it's a 2 times A1 T1 plus A2 T2. Putting a value, it comes like 11,968.7, or you can call it 119.68 centimeter square. Now coming to window KW, window space factor, copper area upon window area. So inside and outside diameter of the LV winding is typically number of turns around typically 57 round of 50 volt, and area of the conductors is 53.33 millimeter square. Let's choose the copper rectangular conductor of size 6.3 into 4.5 as a 2 strip, and let's say paper insulation to be used in this conductor. So let's take the inverse in dimension of insulation of 0.5 millimeter. So now diameter of insulated conductors, putting the value of all these 6.3 plus 0.5 into 4.5 plus 0.5, it becomes 6.8 into 5, that's a 34 millimeter. And rectangular strip conductor dimensions with the 6.3 into 4.5 added to the 0.5. So let's choose 2 layers. Transfer layer in LV winding is 58 by 2, that's a 29, and width of the conductor is 6.8 millimeter along with the height of window 5.5, that's a 10 millimeter along with the width of the window. For 2 layers, the conductor dimension is 6.8 millimeter along with the height of window, and with the 2 conductors 5.5, that is equal to 10 millimeter per width wise, and helical winding is huge. So now coming to space required is 28.1 times the axial length, and axial length of the winding equal to turns per layer into the width of conductor along with the height of window. So that's it, 29 into 6.8, so it becomes 197.2 or 19.72 centimeter. So height of the window is 34.4 centimeter. So clearance is now 34.4 minus 19.72 divided by 2, so it comes 7.34 centimeter on each side of window, and will be filled with the insulation. So using a 0.5 millimeter paper cylinder between layers. So radial depth of the LV winding is now 2 into 10 plus 0.5, so 20.5 millimeter, and diameter of subscribing circle D equal to A upon 0.6, so it 15.82 centimeter. Now using a 0.5 millimeter paper cylinder between the layers, so the radial dimension depth of the LV winding is 2 into 10 plus 0.5, 20.5 millimeter, or diameter of subscribing circle is 15.82 centimeter. So using 1.5 millimeter thick press board insulation between LV winding and core. So inside diameter of the LV winding equal to diameter of subscribing circle and plus 2 into insulation thickness. Putting the value, it comes 16.12 centimeter. Now the outside diameter, that is LV inside diameter plus 2 into radial depth of the LV winding. So putting the value, it comes 20.22 centimeter, and the mean diameter equal to mean of inner and outer LV. diameter of low voltage winding, that's 18.17 centimeter, and mean length of turn is pi into d, so that comes around 7.08 millimeter, and inside and outside diameter of LV winding is maximum number of turns is 2468, and size of conductor is 1.212 millimeter square round conductor. So with the insulation, size of conductor becomes 1.375 with the enamel coating. So let's consider the number of coils in HV winding such that the volt per coil is already 300. So if 8 discs are used and volts upon coil is V1 upon 8, so that comes like a 1375, and turns per coil is N1 by 8, that comes 308.5 or 310 coils or 315 equivalent. So now 7 coils of 315 tons can be used, and end coils of 263 tons can be used. For the normal coil, 15 layers and 21 tons per layer considered results in the maximum voltage between the layers is 2 into tons per layer into ET. So that comes 189 volt. So this is much below the normal voltage of 300 volt between the layer. Now coming to axial depth of the coil, that is equal to number of turns per layer into size of conductor. Putting value, it comes 28.875 millimeter, and axial depth of the end coil is 15 layer and 18 turns per layer. So putting value, it comes typically 24.75 millimeter. Now coming to lattice space between the adjacent coil is 5 millimeter in height. So axial length of HV winding is number of coils into coil depth plus end coil axial depth plus number of coils into space between the coil. Putting value, it comes like 261.875 millimeter, and since the height of window is 344 millimeter, so clearance on either side is your putting value 344 minus 261.875 divided by 2, that is 41.06 millimeter. Now coming to insulation used between layers, is taken 0.3 millimeter thick paper. The radial depth of the HV coil is number of layers into size of conductor plus number of layers minus 1 into insulation thickness. Putting value, it comes 24.825 millimeter. So total insulation between LV and HV winding is 15 millimeter with a backlight paper of 5 millimeter, coil duct of 5 millimeter, and KV insulation of 5 millimeter. Inside HV winding is putting value this 202.5 plus 2 into 15, that's come to 32.2 millimeter, and outside diameter of HV winding is 2. Putting value, it comes to 81.85 millimeter. Now clearance between the two HV windings of adjacent line, that comes around 14.35 millimeter, and this much clearance is considered sufficient for 11 kV. Mean diameter of HV winding is typically 232.2 plus 281.85 divided by 2, so it comes 257.025 millimeter, and length of the main turn of HV winding is pi into d, so it comes like 807.47, that is 0.807 meter, and the resistance of primary winding L1 rho LMT T1 upon A1, putting value, it comes 34.52 ohm. So mean diameter of LV winding, that is mean of inner diameter and outer diameter, so that comes about 161.2 plus 202.2 by divided by 2, 181.7 millimeter, and let's mean turn length of LV is pi d, it comes 570.83 millimeter or 0.5 millimeter. So resistance of LV winding R2 rho LMT T2 upon A2, the value, it comes 0.0126 ohm. Now total resistance referred to primary are equal to R1 plus R2 upon K square. So putting the value here, it comes 58.9 ohm, and per unit resistance R1 R1 divided by V1, it R1T, it comes 0.016 per unit. Now leakage reactance, the mean diameter of winding is mean diameter of HV winding and LV winding. So taking average, it comes to 19.36 millimeter, and length of mean turn is pi into d, so it's 689.13 millimeter. The height of the HV coil, that let the backlight cylinder is used between the LV winding and the core of 5 millimeter thickness. Therefore, the distance between the LV winding and core is 10 millimeter, and there are 8 coils of LV side and 15 turns with 15 and 21 turns per layer. So now the height of the winding over the copper is that height of the HV winding in each disc into number of discs plus height of space factor into number of spaces. So putting the value 21 into diameter of conductor insulation into number of disc plus height plus space into number of the spacer, it comes 301 millimeter. Now height of LV winding, so number of turns In LV coils are 58 in number, and this can be arranged in 2 layers with 29 turns in each layer. The size of conductor of LV winding is 6.8 into 10, and height of LV over copper is number of turns per layer into height of the conductor. So it comes 197.2 millimeter, and mean height of the coil, that is the mean height of the LV winding, HV winding, the putting value, it comes to 49.1 millimeter. So now coming to the ampere turns, so 131.23 into 57, that's a 7,480.11 ampere turns. So per unit reactance is 2 pi f mu LMT 80 divided by L0 80 in bracket A plus B1 B2 by 3 per unit. So here the typically the A distance between LV and L is a 15 millimeter, B1 radial depth of the LV winding 20.5 millimeter, B2 radial depth of HV winding 24.823 millimeter. Per unit reactance putting value all, it comes like 0.0564, and per unit impedance is under root R square plus X square, so it comes 0.05862 per unit. Now coming to typically other applications, there are plenty of high frequency transformer applications like taking a switch mode power conversion, radio frequency transformers, welding transformers. So there are plenty of and power supply of switch mode power converter, including the even LED lighting, then your BLDC fan, and apart from your instrument, computers, laptop, desktop, as well as the lot of chargers used in all accessories, include mobile charger, EV chargers. We use the high frequency transformer. So there are plenty of, you can call it like applications of this high frequency transformer, starting from computer industry to laptop, mobiles, weldings, instruments, electronic instruments, electronic gadgets. So you can see the number maybe even several billions, around the world. And typical growth, you can see even the inductors also used along with these transformers in these all power electronics converter, like a DC-DC converter, as well as other converters. Also we use a lot of inductors in power electronics. Then your inductor used for current filtering of power frequency. And the typically example of high frequency transformer used normally in power supply is the typically like flyback DC-DC converter with the flyback transformer, that you apply DC, you convert high frequency AC, and with the help of flyback transformer you convert it into appropriate voltage and you rectify to get the DC. So it's a virtually isolated DC-DC converter. And here of course the major important benefit is that you are able to provide the isolation. You can get even multiple output. Apart from that, you can reduce the size drastically down by adopting the very high frequency in the transformer order of like a 50 to 200 kilos. Even people have gone to up to 500 kilohertz. Similarly, you have another converter with the two output forward converter, as mentioned, that you can have multiple output also in that case. Like then, so there are a lot of typically DC-DC converter with the isolation where we use high frequency transformer. So for a transformer design problem, it is desired to design a K winding transformer. Both copper loss and core loss are required to be modeled, and as the operating flux density is increased by decreasing the number of turns, the copper area is decreased, but the core loss is increased. Of course, we determine the operating flux density, that minimize the total power. So let's take the total area of copper in window is N to AW, as you can see in the diagram, and area available for the window winding conductors is Ku into AWA, and the constraint is defined by Ku into W should be greater than N into W, and Ku is the fraction of the core window area that is filled by the copper. So now mechanism that cause Ku to be less than 1, the round wire does not pack perfectly, which reduces the Ku by factor of 0.7 to 0.55 depending upon the winding technique, and insulation reduces Ku by a factor of 0.95 to 0.65 depending upon the wire size and the type of insulation, and then additional insulation may be required between the winding. Normally we of course use the lead wire which have a lot of strands into the one turn or one wire, where also every wire takes a separate insulation. So that's the reason this factor goes quite low. So typically value of Kw is 0.5 for simple low voltage inductor, 0.25 to 0.3 for offline transformer, and 0.05 to 0.2 for high voltage transformer, where high voltage you really use again for multiple kV additional insulation, and 0.654 low voltage foil winding inductor or as well as transformer winding. So resistance of the winding is R equal to rho L upon LB upon AW, where rho is the resistivity of conducting material, LB is the length of the wire, and AW is the wire area. The resistivity of copper at room temperature is 1.724 into 10 power minus 6 ohm centimeter. The length of the wire comprising n turns winding can be expressed as LB equal to N LMT, and where MLT is the mean length per turn of the winding and the mean turn is a function of core geometry. So the final equation given R equal to rho N MLT upon AW. So the force constraint is N into I max equal to B max upon into LG upon mu 0. So we get LG from L equal to mu 0 AC N square upon LG, or KW KU WA greater than N AW. So R comes rho N LMT upon AW. So these equations involve the quantity like A, AC, WA and MLT, which are the function of the core geometry, and I max, B max, mu 0, L, KW, KU, R and rho, which are given specification for the quantity, and N, LG and AW are unknowns. So the following quantity are specified using the symbols like wire resistivity rho, unit ohm centimeter, peak winding current L, I max in ampere, inductance L into Henry, N in Henry, winding resistance R in ohm, and window fill factor kW, and core flux density Bm in Tesla. The core dimensions are expressed as core cross section area AC in centimeter square, core window area WA in centimeter square, and mean turn length MLT in centimeter. As you can see here, the application of K winding having a known RMS current and their desired ratio is V upon N1 equal to V2 upon N2 equal to V upon Nk. As you may have a multiple winding into that, as you can see in the diagram, primary is 1 with the N1, but secondary is N2, N3 up to Nk with the current of I2, I up to Ik. Now coming to allocation of window area, so winding 1 allocation is referred to alpha 1 WA, winding 2 allocation alpha 2 W2 WA, etc. And that you can call where the alpha j equal between 0 and 1, and sum of L11 alpha 2 to alpha k should be equal to 1, and that gives the total window area. So now copper loss will be PCU j equal to Ij square Rj. Resistance of winding, jth winding is Rj rho Lj upon Awj, and with Lj equal to N Lj in MLT, length of wire winding j, and Awj is WA KU alpha j divided by Nj, that is wire area and of winding j, and hence PCU j will be N square Nj square Ij square rho MLT divided by WA K2 alpha j, and the sum of copper for overall windings will be PCU equal to PCU1 plus PCU2 plus up to PCK, that is rho MLT divided by WA into KU, and j equal to 1 to K, and j square Ij square upon alpha j. So need to select value of alpha 1, alpha 2, alpha k such that the total copper loss is minimized. And if you can see here, the typical example is here we have a PCU1 and then PCU2 to PCU3 as a variation, so we get PCU total, which get the minimum corresponding to alpha value in between 0 to 1. So for alpha 1 equal to 0, wire of winding 1, 0 area, PCU tends to infinity, and alpha 2, 1 equal to winding remaining winding have a 0 area, so these copper losses tends to infinity. So this is the choice for alpha 1 that minimize the total copper loss. So minimize function is PCU total equal to PCU1, PCU2 of PCUK, that is rho LMT upon WAKU, and j equal to 1 to k, and j square is Ij square into alpha j, and subject to the alpha 1 plus alpha 2 up to alpha k equal to 1, and define function of alpha 1 to alpha k into eta, where PCU total alpha 1 to alpha k plus rho g of alpha 1 to alpha k, where g alpha 1 to alpha k equal to 1 minus j equal to 1 to k alpha j is the constraint that must be equal to 0, and eta is the Lagrange multiplier. So now optimum point is the solution of the system equations, taking a partial derivative of this function with respect to alpha 1 equal to 0, alpha 2 equal to alpha 3 up to alpha k and eta k, and result is your eta equal to PMLT upon WA into KU, and j equal to 1 to k Ij square I2 square PCU total, and Lm is alpha m equal to nm im, n equal to 1 to infinity I, nj ij, and alternate form is alpha m equal to vm im divided by n equal to 1 to infinity bj ij. So, or alpha m equal to vm im upon ni to infinity bj ij. So, apparent power is in winding j is the vj ij, where the vj is the RMS peak applied voltage and ij is the RMS current, and so window area should be allocated as per apparent power of the winding. So, typical example here with the typical taking example PWM bridge transformer, the waveform and RMS value of winding primary and secondary currents are different, assuming that this configuration has a 3-winding transformer case, and you can see the how the current is there of primary and secondary and typically the third winding. So, now you can find out from the waveform, these waveform the value RMS value that comes n2 upon n1 to I under root d, and I2 equal to I3 under root 1 upon 2 Ts 0 to 2s I22 square, or half I under root bracket 1 plus d. These are typical RMS current from the waveform which is shown here, and then an allocation of window area alpha m equal to vm im n equal to 1 to infinity vdj. So, from RMS current expression, fraction of window area allocation of primary winding alpha 1 equal to 1 upon 1 plus under root 1 plus d upon d, and fraction of window area allocated to secondary winding is alpha 2 equal to alpha 3 half 1 upon under root 1 upon in bracket 1 plus under root d upon 1 plus d. So, now suppose to optimize the transformer design as a worst case operating at d equal to 0.75, then alpha 1 equal to 0.396, alpha 2 by 0.306 and alpha 3 0.03, and the total copper loss is given rho LMT, PC equal to rho LMT upon W8 I equal to j equal to 1 to 3 and I and j I j square, and typically rho MLT and n2 square I2 square upon WKU in bracket 1 plus 2d plus 2 under root d plus 1d. So, core loss is given by PF equal to KFE BMP to power beta ACLC. The value of beta for a barite core is 2.6 to 2.7, and maximum flux density BT AC component is Bmax, and increase the Bmax, increase the core loss rapidly. So, typically the design as a basic constraint on design, the flux density related to window winding voltage as Faraday law, applying the voltage volt second to primary winding to positive cycle. So, lambda equal to T1 to T2 V1T into dt. You can see in the diagram. So, this the cause flux is to change from negative to positive peak, and the peak value of flux density for N1 primary terms is given by Bmax equal to lambda 1 upon 2 N1 AC, and the for optimum window allocation between the windings, the copper loss is taken equal to PC equal to rho MLT N1 square into I total square upon WKU, and I total equal to in bracket j equal to 1 to 3 and j upon n1 into I square. Total copper losses can be expressed as PC equal to in bracket P lambda 1 square I total square divided by KU and MLT upon AU AC square into 1 upon Bmax square. The copper loss decreases rapidly as Bmax increase, and the optimum value of Bmax for optimum power loss is P total equal to PFE plus CU, and PFE equal to M PFE B max P AC into and PC equal to in bracket P lambda 1 square I total equal to KU MLT upon WAC square upon into 1 upon BM square. And as you can see in the diagram, how the your copper loss changes and how the your core loss changes and how you get the minimum total loss for the design of this transformer. So, now coming to example as a flyback transformer. So, you can see the diagram with the flyback, how we design and how the winding currents are there, voltage and currents are there, and how the your typically the BS loop for Faraday core is there. So, now taking a typical example of a small air gap here, so solving the magnetic circuit, N equal to phi RC plus RG, for RC much greater than RG, so N equal to phi RG, and where RC equal to LC upon mu C into AC, and RG equal to LG divided by mu 0 AC. So, now coming to typically maximum flux density, the given a winding current I max, it is desired to operate the core flux density at a peak flux density of P max, the value of Bmax is chosen to be less than worst case saturation flux density of core material, and from the solution of magnetic circuit N equal to B AC into Rg, and let I equal to Imax and B equal to Bmax. So it comes N Imax equal to Bmax AC Rg, that is equal to Bmax Lg upon mu 0. So now coming to typically the converter operates with the input voltage of 200 and produces a full load of 20 volts at 5 ampere. The switching frequency is 150 kilowatt. Under these operating conditions, it is desired the converter operates in the continuous conduction mode with a magnetizing current ripple of 20% of the DC component of magnetizing current, and duty cycle is chosen to be 0.4, D equal to 0.4, and the turns ratio is N2 upon N1 equal to 0.15. So copper loss of 1.5 watt is allowed, and field factor of Ku equal to 0.3 is assumed. The maximum flux density Bmax is 0.25 Tesla is used for ferrite core, and it is less than the saturation flux density of ferrite core material, which is around 0.4. So using the typically capacitor charge balance, the DC component of the magnetizing current is found. Im equal to N2 upon N1 equal to 1 upon 1 minus D V upon R. So it comes 1.25 ampere, and hence the magnetizing current ripple should be Im equal to 20% Im, that is 0.25 ampere, and at the maximum value of magnetizing current is your Im equal to Im plus delta Im, that is 1.5 ampere. And now obtain this ripple, the magnetizing inductance is Lm equal to Vg dTs upon 2 Im. So that comes 1.07 millihenry, and the RMS value of primary current is found to be from formula I1 equal to Im under root D in bracket 1 plus 1 upon 3 delta Im divided by Im square. So it comes 0.796 ampere. So the RMS value of secondary winding current is found similar way, that is I2 equal to N1 upon N2 Im under root D dash in bracket 1 plus 1 by 3 Im delta Im upon Im square. So it comes 6.5 ampere, and I2 is not simply equal to the turns ratio multiply I1. So total of winding current is to be I total equal to I1 and 2 upon N1 into I2, that comes 1.77 ampere. So now to evaluate the necessary core size, Kg greater than rho Lm square I total square and Im square by B square PCU Ku, putting the value it comes 0.049 centimeter square, and the smallest E core that certify equality is the E30, which has Kg equal to 0.0857 centimeter. So dimension of this core are AC equal to 1.09 centimeter square, W equal to 0.476 centimeter, MLT 6.6 centimeter, and LM equal to 5.77 centimeter. And the air gap is chosen for like Lg equal to mu Lm Im square by PM AC, putting the value it comes 0.44 millimeter, and number of winding terms is chosen for formula. So N1 equal to LMT Im upon Bm AC into 10 power minus 4, putting value it comes 58.7 ton. And since the integer turns to be required, so this value round up to N1 equal to 59, and to obtain desired turns, the N2 chosen N2 turns ratio into N1, it comes 8.81. So now this value is round up to N2 equal to 9. So fraction of window area is allocated to winding 1 and 2 according to the equation. So alpha 1 equal to I1 upon I2, putting value it comes 0.45. L2 equal to N2 upon I2, N2 into I2 upon I total, it comes 0.55. So wire gauges are therefore AW1 less than alpha 1 Ku W upon N1, 1.09 10 power minus centimeter square. So it comes 28 area wire gauge, and A2 is alpha 2 Ku W upon A2, that comes 8.88 into 10 power minus 3 centimeter, it comes 19 wire gauge. So now coming to typically another example of single output isolated Cuck converter. As you can see the diagram, so we have a transformer here. So the rating is 100 watt and duty cycle 0.5, and Ku is 0.5, and switching frequency 200 hertz, and turns ratio is 5, and allowed P total is 0.25 watt. So now the loss parameter with the farad cores are Kf equal to 24.7 and B equal to beta equal to 2.6. So this is typically the example of waveform. Because of 50% duty cycle, these are the waveform of primary voltage, primary current, and then the typically the secondary current. And applied primary volt secondary is lambda equal to dWs Vc1, putting a value it comes 62.5 volt per microsecond, and applied primary RMS current I1 equal to 1 root D I upon N square plus D dash Ig square, so it comes 4 ampere. Applied secondary RMS current I2 equal to N I2, that is 20 ampere, and total RMS winding current will be I total I1 plus 1 upon N into I2, it's 8 ampere, and kgfe force, that is core area, that is putting the value in the formula, it comes to 0.00295, and the pot core data list 2213 pot core with the kgfe equal to 0.49. So next small pot core is not large enough. So now considering the typically the peak plug density Bmax equal to putting the value comes 0.0858 Tesla, and this is much less than the saturation plug density of 0.35 Tesla. Value of Bmax is the vicinity of 0.1 Tesla, or the typical Faraday design that operates at a frequency in the 100 kHz. So N1 equal to putting a value of the data that comes 5.74. So N2 comes N1 upon N, that's 1.15 tons. So now the value of N1 is 5 and N2 is 1 taken, but this will lead to a slightly higher plug density, a slightly higher loss. So fraction of window area allocated to each winding, since it's considering the example of ratio of winding currents is equal to the turns ratio, so equal area allocated, alpha equal to 4 upon 8, that's 0.5, and alpha 1 equal to typically putting the or 20 by 5 divided by 8, that's 0.5. AW1 equal to putting value, it comes like a 14.8 into 10 power minus centimeter square. So AW external wire gauge 16 and AW 2.5 divided by, so it comes 74.2, 10 power minus 3 centimeter square, wire gauge of 19. So typical example is wire now sizes, primary is 5 tons of 16 gauge and secondary is 1 ton of 9 gauge, and with a very large conductors, 1 ton of 9 wire gauge is not practically feasible. So hounds of file winding and least wire parallel strands of can be used. Now coming to multi-winding transformers, which are used typically for many applications. The one of the typical applications is to have a multiple, primary is one, then you can have a multiple load for power frequency transformer, or you can use in the rectifier transformer. They are very used for in the rectifier, control rectifier as well as like in HVDC, and they are used typically, in case of your medium voltage drive as a rectifier. So diode rectifier as well as it's also used electroplating, electromining industry for multipulse converters, like, so they are very much used in fax devices to step up the voltage of power converters at which are designed optimum voltage, but you have to go for HVDC or as well as the fax devices typically of transmission voltage of 400 or 500 kilovolt. So there we need of course the transformer of typically of step transformer very large rating with the of course with the multipulse configuration for voltage source converter as well as typically with the your diode rectifier and thyristor converter. So diode rectifier will considered as a major contributor to generate the harmonics on both AC and DC side, because it draws a non-sinusoidal current from the AC mains. And this results in increasing the total harmonic distortion of AC mains voltage because of the voltage drop due to harmonic current flowing through the system impedance and poor power factor. Increasing the current cause the equipment overheating because of the harmonic current absorption, overheating of the transformer, overstressing of power factor correction capacitors, because they draw the very harmonics, they suck like anything, and decrease rectifier efficiency and variation in DC bus voltage due to fluctuations in AC mains voltage. So the term multipulse converter generally means a converter providing more than 6 pulses of DC output voltage per cycle from the 3-phase AC mains, and these multipulse AC-DC converter are connected in such a way that the harmonic produced by one converter is cancelled by the other, thus leading the harmonic elimination of the input AC mains. And to deal with these harmonic issues, multipulse methods are very much effective the power electronics industry because of their simplicity, reliability, and excellent performance in improving the power quality. And the technique of 18 pulse AC-DC multipulse converters eliminate the harmonics of the order of 18 n plus minus 1 and improve the power factor. The typical example of 18 pulse converter here is with the delta polygon winding. We have a different kind of winding connection for converting this kind of concept, like we have a not only star delta connection, but we have a hexagon, polygon, T connection, Scott connection, zigzag connections. So plenty of 7 to 8 type of connection are required for giving a phase shift as well as providing multi-phase. So here for 18 pulse, we have a primary delta connected, but secondly we have a one is delta connected with the 0 phase shift, and other two windings are with the plus 20 degree and minus 20 degree with the polygon connections, as you can see here, which taken as a segment of the winding for all 3 phases, typically in the secondary. You can of course develop as a one unit of 3 phase transformer, or you can have a 3 single phase transformer and connect in this manner to have a 18 pulse from this rectifier. Of course, you can add the voltage or you can connect them in parallel. It depends on the voltage and current rating on the DC side of this rectifier arrangement. So, typical example of design of secondary of 240 volt DC link voltage or DC link voltage and line voltage of DVR is calculated VL equal to pi d upon 3 root 2, that is putting a value 240, it comes like a 177.68 for delta winding, and delta polygon it comes VLL upon sin 120 divided in equal to VNL upon sin 40 or VNS upon sin 120 delta polygon. So you can get VNS equal to, that is typically the winding zone here, it is sin 20 VL upon sin 1 to 70.17 volt, and VNL as shown this voltage for this sin 40 is VLL 120, it comes 131.877 volt for giving the phase shift of plus minus 20 degree. So typical example, this is a waveform which we got it after developing this delta polygon transformer for 18 pulse. You can see how the typically individual rectifier waveform looks like, and how the combined winding typically currents of II, IB, supply currents are shown here, and the typical, you can see the TAD comes of these currents order of 4.6 or order of that in the supply side. So now this is another transformer with 36 pulse converter. As you can see, the phase shift provided here for different 6 rectifier of 6 pulse. Primary extended delta of plus minus 10 degree of T1 and T3, and each transformer have a delta and star configuration secondary winding, and 6 pulse diode bridge rectifier is connected at the output of each secondary winding. And now typical example, as in the same way, you can have a primary extended delta with the typically phase shift required for 10 degree, and secondly you have a delta and star with the typical turns ratio, shown here with the theta as a 30 degree phase shift between delta and star. And this is another connection typically for providing the phase shift, how you really design the transformer for 36 pulse converter. And then you can say the primary winding voltage, the neutral line voltage is 1.8. The property of this triangle, as you can see, is a 415 volt grid. So you can find out the typically you can call it the turns ratio, and then the primary voltage PP1, and then the smaller winding voltage order of 210, so or NP2, the fraction of turns. So this gives the design calculation from simple geometrical relation. Now coming to secondary winding of the 200 volt DC link, so correlation between the line voltage and DC voltage is VLL pi d upon 3 root 2, it comes 148.0. Considering the second delta winding, it comes VLP equal to 148, so VP it comes VLL on root 3, so it comes 85.49 volt. So next, the typical example here we can say for the 12 pulse converter, let supply voltage is 415 volt, you can see 50 hertz, and load current is 400 ampere, DC voltage 2 to 2.2 kilovolt. The total DC voltage across the series connection thyristor is your 2.2 kilovolt. So DC voltage across each single thyristor converter is 2.2 divided by 2, that is 1.1 kV. And now you can find out VDC1, that is 3 root 2 bar pi VL cos theta. So it comes 1.1 into 10 power 3, and VL equal to, from this relation it comes like 940.5 volt. So VL of 9.4 secondary side of the transformer. So primary transformer, secondary winding of the transformer connection is star. So voltage of the secondary transformer is VNL equal to VL upon 3, that comes 543.0 volt. And the line current of the secondary side is 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 equal to root 2 by 3 IED, comes 326.5 ampere, and the phase current of the secondary side of delta is your phase 326.5 divided by root 3, that is 188.5, and turns ratio comes N1 upon N2 from the voltage, it comes 0.76, and transformer ratio N2 upon N3, it comes 0.44. So now the IRMS current of primary winding is IPH N2 upon N1 into I star plus N2 upon N1 I star delta. So putting value it comes 810.5 at the angle of minus 15 degree, and IL primary is root 3, that's 1403.8 ampere. So KV rating is half summation of 3 into VL and I phase by 3. So putting the value of all, it comes 1036.3 kVA. Now coming to computer design of transformer. By design of transformer, it means that I am mentioning the transformer of given specification. So by design, we mean the synthesis while calculating the performance for a given geometry is called analysis. So design synthesis uses the analytical iteratively. Analysis implied a mathematical model. So mathematical models may be field distribution using finite element type or circuit type, as finite element models are computationally time probative. So they are in most cases used for performance validation after the design optimization based on analytical model. Hence, we approach the preliminary general transformer design by way of case study of making full use of transformer parameters, rather realistic expression of the circuit model, and already devised here. As you can see how the FEM model gives the and how the analytical model equivalent circuit is there of the transformer with the different parameters of equivalent circuit. So typically the design covers the wide span of practical effort from an infinite initial sketch or a plan to weld real drawing, a prototype or installation. And design is something between an idea and product. So what design can describe the process as well as the state of the process. A design can have specific orientation or the site of improvement such as design for manufacturability, electromagnetic compatibility and reliability and so on. So a design problem have to be formulated considering the various constraints, process, availability of material and quality aspect like cost aspect. And design normally requires considering the design requirement and to look for the best solution, which additionally an optimization process where the targets such as lightweight, construction, cost efficiency, reliability or some other requirement are focused on. So the problem described earlier may be solved separately and then results combined later on. So additionally, each of these problems may be further divided into simple but loosely related elements. So each element may then be considered as a separate problem, and then procedure may be involved in the solution to some of the elements may many times over the arrive to at acceptable solution. So we start from design, then the design of different part 1, part 2, and then analyze and combine solution. So the other aspect of the present design of element electrical machines designing the set of models, all of which form part of single system. Designing in a isolation or in parts can be rebel or could be distressous. Therefore, the system cannot be isolation and need to be designed concurrently, since the design of one part is closely related to the design of other part. So coming to design part 1 and then analyze and go to back if required, and part 2 then analyze and go back, and the part 3 and analyze, design and come to final solution. So it is clear that the design is an iterative process wherein assumed data may have a variety many times to arrive at the desired design. The evolution of design to meet is specified optimum criteria is a matter of long and tedious iteration, and this is the biggest factor which led to the widespread use of digital computer for the design process. So computer design eliminates the tedious and time-consuming hand calculation, thereby releasing the designers from the numerical complexity to enable him or her time to grapple with the physical and logical ideas, thereby accelerating the design process. So now the advantage of this computer design has the capability to store amount of data, count integer, round the results, down the integer and refer the table to graph as other data. As you can see here, the how the characteristic are shown, how the VH curve data are there, how the your tabular data are really there to be. So the CAD makes it possible to select the optimized design with a reduction in cost and improvement in performance as you go to many iterative process, as you can in the typically with the different variables and typically the temperature. So a large number of loops can be incorporated in the design program, and therefore it makes it easier to compare different design, out of which the best suited can be selected as the process with the start, design problem estimation, initialize of key parameters, then calculation of electric properties, efficiency estimation, calculation of typically the total weight, then MF calculation, then calculation of constraints, and then go to better solution otherwise. And now it performs all arithmetic operation at a high speed and makes it possible to produce designs in a short time. It is capable of automatic operation going from one step to another without the attention of operator, and reduces the probability of the error, with the result of highly accurate and reliable results are obtained. So the larger manufacturing saving can be obtained by optimization of design. This optimization is economically feasible only through the use of digital computer. So it is capable of making logical decision by itself with the program into, thereby saving the man hours of design engineers, which can be utilized for other gainful work. So the application of digital computer is the to the problems of electrical machine design was first introduced in 1950. An early work done by Murray and Williams in 1956 transformer design, Rhodes in 1959 analysis and synthesis method, and Wiener 1959 of 4 induction motor, and Goldwyn typical 1959 optimization in electromagnetic design. Rose in 1950 introduced the concept of two commonly accepted approach to design process. First the analysis method and second is synthesis method. So design by analysis, the use of terms analysis method means the use of computer is only for the purpose of analyzing. Analysis leaving all the exercise of judgment to the designer. And the typical process here that they start human decision, then input, performs calculation output, and then take a decision. So in this method, the choice of dimensions, material, and types of construction are made by the designer, and these are presented to the computer as input data. The performance is calculated by computer and returned back to the designer for him or her to examine. The designer examines the performance and makes another choice of input if necessary. The performance is recalculated, and this process is repeated over and over again till the performance requirements are satisfied. Now, the advantage of this design by analysis is it's fairly easy to program, to use and understand. It results in considerable time saving, thereby giving a quick return on the investment made. Then the programs made upon the analysis method are simple but become the foundation for larger and sophisticated program, and the results of analysis method are generally acceptable for designer. Now, another process is designed by synthesis. As you can see the flow chart, all the decisions are taken by typically by the computer by logical decision or other than calculation. So performance calculation assume suitable value, then result calculation, performance calculation, compare and performance and the performance sensitivity. If not, adjust the value of variable and or calculate the total loss, then print design and file. So here, how in step the desired performance is given as an input to the computer, and logical decision required to modify the value of variable to arrive at the desired performance are incorporated in the program as a set of instructions. Unlike the case of analysis method, program or computer runs is therefore not interrupted for the designer to take logical decision. And the synthesis design should be such that it produces an optimal design as desired, and synthesis without optimization has not much meaning. So greatest advantage of synthesis method is the saving in time in labs and engineering man hours on account of the decision making left over the computer itself. Now, the coming to design optimization. The optimization is a collective process of finding a set of conditions required to achieve the best result for a given situation. So here you can say about the design expert in electric machines or device optimization. So you require typically the optimization technique for solving the problem, like a distribution, like gradient based, historic based evolutionary algorithm, and problem formulation is like a method of engineering object design, defining the objective function, constraint, geometry parameter, and aspect like automation, like cluster and environment, and then machine and device modeling like method engineering, then machine device evaluation for analytical and finite element, and multi physics aspect like thermal and rotor dynamics, and like typical power electronics control, and classical machine design as material electromagnetic winding design. So now coming to design by hybrid. Hybrid method is incorporated the use of both analysis as well as synthesis method in program. Synthesis as a minor problem, more costly, and analysis major problem. Now coming to like a scope of design. Typical example is the power is typically milliwatts to megawatt and frequency 52 megahertz, and type is like a single phase or three phase high frequency, and primary any number of windings or taps, and secondary is number of secondary winding and taps, and so 6 shield is required. Then voltage limit per winding, current limit per winding, and voltage regulation any value within the practical limit. Now scope of design, temperature rise any value within the practical limit, ambient temperature any value within the practical limit, DC voltage level for each secondary winding, and insulation requirement like winding margin, winding layer insulation, insulation between winding, coil web insulation, winding in sequence, type of winding, and coil cased or open construction. Now coming to core type like EI laminations like 21 standard type, unlimited number of non-standard or specified, or C type like 30 standard type, unlimited number of non-standard or specified, or 3 phase lamination like 15 standard types or 3 phase core 30 standard type, and core material 24 M2, 29 M6, 29 M19, 26 M19 or 0.06 vanadium, pyramidal 29 M15, etc. Now flux density like designer choice or computer selection, and mode of design like computer design synthesis or automatic mode, or manual design by analysis method, or size directed design by hybrid method. Now coming to objective function, the objective functions of transformer design could be minimize the overall cost, including the cost of material, labor and losses, maximize efficiency, power output or regulation, and could be single objective or multiple objective function. The constraint, maybe the constraint for transformer design could be transformer transferred power, impedance, possible flux density for that material, like a saturation limit, and physical dimension of the machine like winding. Now the design of transformer. Computerized design of transformer uses the same philosophy as those followed by experienced designer. So once the input information such as kVA rating, percentage loss, percentage impedance, etc. given, the computer assumes initial certain design parameters such as maximum flux density, maximum current density, and space factor. These parameters are necessary to calculate design data and performance characteristics. Now coming to the output performance is compared with the desired output. If calculated values exceed the desired one, the initial assumptions are revised and processed till the favorable design is built. So now coming to as a typically the process, as you can see flowchart of designing the transformer. So a complete computerized design for large transformer is illustrated with a typical flowchart with 15 subroutines. Subroutine SR1 include all items generally specify the design as per need and contains maximum rating of transformer, number of phases, frequency, LV, HV, line voltage, LV, HV, winding connection, arrangement of winding with respect to limbs, percentage tapping, maximum pressurized of percentage reactance, percentage loss as continuous maximum rating, and subroutine SR2 the designer sets maximum or minimum limit of quantity like maximum core flux density, maximum LV, HV current density, radial distance between LV and winding, C0, maximum core height, maximum and minimum percentage LV and HV tapping, maximum percentage LV, HV ID current losses, then breakdown insulation of winding, specific weight and specific cost of load and iron loss, and such limits serve two purposes: to modify the program when the calculated quantity goes beyond the limit, and if the modification is beyond the scope of program, it to enable the designer to modify the limit and program is diverted to exit. Now coming to subroutine SR3, compute LV, HV current from the rated power, the number of limbs found, line voltage, winding connection, and program calculate the limb currents and voltage. SR4 choice of KE, KF, KW are introduced to enable computation of AT, ACON, AW, AT, T1, T2 for maximum flood density current density. Subroutine SR for SR6 selection of nearest core section, modify AT and further optimization of core section. Then clearance C0 between LV and winding is assumed. SR3 deals with the LV winding. Then SR8 concerns the HV winding design, and design is checked for impulse strength criteria. Corrective changes are made mainly in the clearances, and operation is repeated unit impulse test criteria certified. The copper and iron loss calculated in SR10 and 11, and the copper loss is varied by increasing or decreasing the conductor size, and iron loss by the core flux density. When these two results are certified, the program calculates the eddy current loss percentage in SR12, and if these are smaller, then the computer go to subroutine SR3. Otherwise, the only alternative is to increase the interwinding clearance C0. Increase C0 results in increase the winding height. Thus, radial depth C1, C2 are reduced to maintain same reactance. The SR3 computes the percentage reactance. SR4 calculate cooling system. SR15 is for weight of core and conducting material cost. Now coming to example 1, develop an algorithm for appropriate formula to calculate the percentage voltage regulation, versus load, primary and secondary current, efficiency versus load, losses versus load, to compute the above at different power factor 0.6, 0.8 and unity, lead lag and condition for single phase 4 type transformer at rated voltage. You can see for load variation 5% to 15% with increment of 5%. So here typically the flow chart, we give the rated voltage frequency and equivalent circuit parameter, and we vary X the 5% from 1 to 150%, and then we go for power factor selection and calculate the typically the voltage regulation, then calculate the typically primary and secondary current, and calculate efficiency, then loss calculation, and then we look into up to whether we have gone full. If yes, then we really go to plot required for all X and power factor values. And this is the typical code for the example what really we talk about in typically in MATLAB. Now coming example 2, develop algorithm to compute the ratio of areas, gross and net area of core and typically area of circumference fill, percentage fill, and dimension of core transformer having 2 to 11 steps in step for optimum design of transformer. So you can just see how it is the core with a square section, then 2-step cruciform, and then 3 steps, and you can go for multiple steps. So square section, cross section is A is equal to A square, and small a equal to 0.707 d. The optimum fill is 0.07 d square upon pi d square by 4 into 100, that comes 63.6, and 2-step core which is called cruciform, and cross section A is equal to A1 B1 plus 2A A2 B2, and where the after solution comes A1 equal to 0.85 d, A2 B1 0.5268 d, and B2 equal to 0.11 d, and optimum fill is comes A 1 pi d square by 4, that comes 78.6. So now you can see going to from square to 2-step we are able to use from 63.6 to 78.6 space. Like now 3-step, so for 3-step A1 equal to A2 plus 2B1, and A2 equal to B1 plus 2B2, and A3 equal to B1, and cross section is AC equal to A1 B1 plus A2 B2 plus 2 A3 B3, and after solution comes A1 equal to 0.906 d, A2 comes 0.707 d, and A3 comes 0.423 d, B1 comes 0.423 d, and B2 comes 1.42 d, and B3 comes 0.1 d, and optimum fill AC pi d square by 4, it comes 85.1%. So you can see that clearly now using more steps we are able to go now utilization to 85%. Now this is the typical example. For increasing the number of steps 4 to 11, the following charts display the strip width and the optimum fill percentage. So we go, for number of steps starting from fill going to 4 steps 88.5 to 95.8%, with the different dimensions go to form. Typically 11 steps means 11 dimensions. It is evident that for 11 steps about 96% of fill is obtained, beyond which the increase in number of steps does not give typically generally satisfactory to increase assembly and inventory cost. And coming to this, for this purpose we just go initial design, and then we go begin with the core design subroutine, then calculate the enter the dimension as dks, and then we look at s equal to 1 yes, then we just calculate the dimension a, and then no, then we go to step 2, then or step 2 or up to step 11 and calculate the core dimension, and we come to convergence. And this is the typical code for calculation for this what we really explain about, and this is the typically the design flow chart for the transformer as which is reported in this publication. So the calculation of eddy current loss and the surface impedance using finite element is done due to eliminate the performance of large power transformer. Example is considered a transformer with a rating of 90 MVA with 3 phase 132 by 33 kV mounted straight side mild steel tank, and this is typically a reported of contour plot of this stray loss curved tank of 500 MVA unit. Like these are used using a finite element analysis in the publication reported. So now coming to this finite element method simulations to optimize the application of magnetic field shielding in the power transformer are performed, and the investigation accounts the effective parameters influence on the magnetic shunt design for the objective of controlling the leakage flux, reduce the generator losses and noise in the transformer, and FEM finite element simulations are successfully used to calculate the flux in the shunt and to indicate the onset of flux saturation and constraint of option for the shunt design during the overloading condition. And here you can see optimum shielding design of losses, noise reduction, and in power transformer reported in typical publication form. So the finite element model is constructed to understand the physical phenomena in power transformer and the electrical fault, short circuit, arcing, lighting, destroy, and quantity of mechanical consequences using computer design tool for the design of and prevention of the fire and explosion, and use the typically the global finite element model to study power transformer behavior during the inner electrical faults, application, explosion. Here typical example is of 150 MVA transformer geometry and winding matching and temperature evaluation after the short circuit. So now typical coming the work here which is reported deals with the determination of susceptibility of different 3-phase transformer cores against GIC, and the result on bypassing the transformer design, and the GIC effect on large transformer is evaluated. It's a zero flux return in transformer configuration, simulated in PSCAD and EMTC, and investigation reported in the typically in the from the transformer industry. Now coming to objective questions, what are the effects of making limbs section lower than yoke section? Really provide the economy in copper, decrease iron loss, decrease, and then what is the effect of increase in height of a window compared to width? Typically cost of copper is reduced as well as the voltage regulation is decreased. Then under the which underlying hysteresis loss is decreased when the thickness of lamination is increased by 10%. The transformer with the rise in supply frequency, copper loss remains unaffected by increase. Under which situation transformer can slightly more overloaded by if ambient temperature is much below the design and if the frequency is increased. The transformer having a highest leakage reactance lead to limiting the induced current of circuit. If leakage reactance of the transformer is proportional to square of the number of turns and added of cooling tubes of the transformer time improve the capacity because of all this dissipation convention increase additional dissipation of radiation, additional cooling circuit. The conservator tank along with the main tank of transformer is mostly adapted to prevent the formulation of tank, and mineral oil can be adopted for transformer cooling. The heat dissipation by means of radiation volumetric transfer the cooling about 0.6 watt per meter per Celsius. Temperature change, tap changer is normally provided on high voltage winding because of lower current. In which of the following relation must be specified in terms of having a constant for weight of iron upon weight of copper, that is loss specific cost of copper divided by specific cost of iron. The criteria for transformer to be designed for minimum volume is volume of iron equal to volume of copper. Large value of current density can be adopted. Transformer applying water cooled, and the heating dissipation capacity of transformer exceeding 50 kV rating is typically cause all fins required all tubes radiator tank on typically combustion, and supply transformer oil may be devised of even by sulfur, moisture and acid, and transformer oil should be typically have a property of high flash point and high electric resistance, and how much heat can be dissipated by natural means of plain fault time 12.5 watt per meter square. Now coming to some subjective questions. What are the essential property of transformer steel? Transformer steel should exhibit high permeability, high resistivity and low coercivity, and mention the type of the winding generally used for low voltage, helical winding and cylindrical winding insulation, and mention the insulating material that is used in transformer, passboard, porcelain, cable paper and insulating. What are the standard conductor used for winding transformer? Standard conductors are used for winding the transformer to reduce the eddy current losses within the conductor. Why the essential property of insulating aluminum transformer? Sufficient mechanical strength withstand stresses, high electric resistance to prevent breakdown, and good oil absorbing capability. Why standard conductors are required? Transpose. It is essential to transpose the standard conductor to equalize the reactance of the stand. Why the power transformer are designed typically to have maximum efficiency at near full load, where the distribution transformer are designed to have maximum efficiency at lower load than the full load. Power transformer are designed to have maximum efficiency at near the full load, where the transformer are designed for maximum efficiency at quarter load. Then, since the power transformer are allowed to work at near full load and switch off and during light load, but the resistance are required to work all the time, including the light load hour. Why the circular coil are always preferred over the rectangular coil? Have a following advantage over the higher mechanical stability over the short circuit condition, and due to the presence of radial forces, there is no tendency to coil to change its shape due to mechanical forces. Proper utilization of ease of firing. Why the step core is used in transformer? Step core is used to approximate the core section near the circle. There reduces the length of mean turn diameter, reduction in the amount of copper. Why stepping is not employed in yoke? The stepping in yoke is portion where the winding is not present, as the yoke portion does not carry the winding, so it is not stepped. In which type of transformer leakage reactance can be varied over the cell type of transformer, which winding can be adjust the leakage reactance. How the transformer dimensions are fixed based on overall dimension of the transformer. The dimension of the tank are decided by the dimension of the transformer frame and clearance required on all the sides. The clearance on the side depends on the voltage and power rating of the winding. The clearance at the top depends on the oil height above the assembled transformer and the space for monitoring the tunnel and tap changing gear, and the clearance at the bottom depends on the space required for mounting the transformer frame inside the tank. So these are the typical references which you followed for preparing this material. You can have a further study from these references. Thank you very much.